Okay, welcome to week 2. So we're going to start talking about one sample t methods. So this is when we have a single population and we're looking at a mean, or possibly when we are looking at matched pairs. So this should be a little familiar from 201 towards the end of the 201 term. So the example we're going to use throughout at least this lesson is about sleep deprivation. So absolutely, if you're not getting enough sleep and good enough sleep, it can absolutely impact a bunch of parts of our lives. It can affect cognition and optimal brain function. You're just not going to do as well if you don't sleep. And obviously, being students in college, this comes up a lot. A lot of folks aren't getting the sleep that they need. It's a big deal, especially if you want to be a student with good grades. So they go ahead, at this particular university, they take a simple random sample of 61 students, and they ask, well, how many minutes per night do you get of sleep on average? So, like last week, how many minutes of sleep did you get on, the average night? So, the students, those 61 students, they reported getting an average of 455 minutes of sleep with a sample standard deviation of 88 minutes. So it fluctuated a little bit. So we might want to estimate what the average amount of sleep students at this university are getting, calculate a 90% confidence interval for the true average amount of sleep per night for students at this university. So before we go too far, we're going to want to look at our conditions. Because if we don't meet our conditions, we can't use the methods that we've been using. So, was the sample obtained using a random mechanism? Translation. Was this a random sample? This is important because if it's not a random sample, we can't say that the sample represents a bigger group. So, yes, in this case, it was a simple random sample, so we can say yes. Then we want to know either if the population of, so if I took all students' average amount of sleep and put them into a histogram, are those roughly normally distributed? Or do I have at least a big enough sample size that I can count on that central limit theorem to kick in? So remember, usually if our sample is at least 30, we're going to be good. We are going to be good because we have a large sample. We have a sample of 61. So even if we found out it was pretty skewed in the population, a sample of 61 would probably be okay. And then here's where things get kind of tied up. Do we know the population standard deviation sigma? No, it did not say that in there. So we had sample information. We had a sample mean and a sample standard deviation. We did not have any information from the population itself. So this is where t distributions come in. So before we were using z methods, so we would have like a z statistic or use like a z-star critical value to calculate the confidence interval. When we don't, we kind of use the z distributions, cousin, which is the t distributions. So if we don't know sigma, so we don't know how it's spread in the population, we're going to have to estimate it using the sample standard deviation. So if we don't know the population standard deviation, use the sample standard deviation as a starting point. So things that are important though is if I only have sample information, I'm now using t methods. So my instead of using a z-star critical value, I need a t-star. So z-star, now we need a t-star. So you need to usually use a t-table to find these. Specifically, a t-table within the sample size will matter, n-1 degrees of freedom. So I found this online. I kind of want to brag. I didn't make this myself. I found this, so there's someone at least as nerdy as me out there. Mr. T-Test. I pity the fool who doesn't know his population standard deviation. Yeah, it gets a little long there at the end. So t distributions, looking here, they look a lot like the normal distribution. They're bell-shaped, they're symmetric, and They're centered at 0, just like the standard normal distribution. The big thing is, so they're going to be a little bit wider in the tails. I had a teacher who called them fatty tails. So there's more area in the tails of t-distributions than there is of the normal distribution. So they're a little bit shorter here in the middle, but they're wider in the tails. And however, the bigger your sample size gets, the closer and closer, like the taller it gets in the middle and the shorter it gets at the end, the closer to a normal distribution it gets. So yeah, they are known for having thicker tails than a normal distribution. Essentially what this means is you're going to have more extreme results, like you're going to have a more extreme test statistic. It's going to have to be further away from 0 in order for us to end up projecting here. So here, which distribution would be more spread out, so have thicker tails? So if we have a t-distribution with 25 degrees of freedom, or a t-distribution with 10. And I'll give you a second here. It's a great place to pause, then I'll answer. So here, we know that the bigger our sample size gets, the taller in the middle my t-distribution will get. And so then the shorter in the tails. Obviously, I'm not going to quit my day job to draw these by hand. But it's going to get taller in the middle and it's going to get shorter or smaller in the tails. So the higher n gets, the thinner the tails get. So 10 degrees of freedom, that has a smaller sample size. So it's going to be B. The t-distribution with the smaller degrees of freedom will have the thicker tails. The t-distribution with the higher degrees of freedom will have the thinner tails. So constructing a confidence interval, it's going to look extremely similar to when we were doing this with z-methods. So I like to put parentheses here. It just helps remind me to do the multiplication first. So we're going to have our point estimate, which is x bar, so the sample mean from the sample, plus or minus, and then we'll have t star. And this will change up. This value of t star, it's going to matter what our degrees of freedom, so what our sample size is, as well as whether we're doing a 90, 95, or 99% confidence interval. It's going to use S instead of sigma. We don't know sigma. If we know sigma, skip straight to using z-methods and a z-star. But if we only have sample information, we have to use t-methods over the square root of n. So it's going to look really, really similar to when we had z-methods, except now we have t-star and S instead of z-star and sigma. So this is just an example here. This table, it shows us, okay, well, if we want to have a 90% confidence interval for a scenario where we have 9 degrees of freedom, this is our t-star. If we want to have a t-star when with 40 degrees of freedom, it's 1.684. You'll notice z-star is equal to 1.645. The higher our degrees of freedom get, the closer and closer t-star is going to get to 1.645. T-star is always going to be at least a little bit bigger than z-star. That's how it works because of the thicker tails. So note on degrees of freedom, we talk about them a lot without really talking about what they are. Absolutely, these have to do with the shape of the t-distribution. As our sample size gets higher and higher, the middle of the t-distribution gets taller and the tails get thinner. So if we have a t-distribution that has n-1 degrees of freedom, the notation we use is this t, and then instead of writing n-1, we could write the number. So if I had a t-distribution with degrees of freedom 9, I would write a t9. Oops, that looks like a Q. T9. So why do we need these degrees of freedom? For starters, we need to account for our sample size, right? We don't want it take credit essentially for having a really large sample if we don't. They're almost kind of like little penalties for having a really small sample size. And it's really, really important to not assume everything's perfectly normally shaped when we have very small sample sizes. But so we're using this because not only are we using X bar to estimate mu, so X bar estimating mu, now we're also using our sample standard deviation to estimate sigma. So since we're like double estimating here, we need these degrees of freedom to kind of help us. Our interval is going to be less precise. Less precise means wider. It may not be a lot wider, but it's going to be at least a little bit wider now that we're using t-methods instead. And this, once again, it accounts for sample size. So the more observations we have, though, the narrower we can get our confidence interval, which is a good thing. We usually want a narrower confidence interval if we can get one. We love it when we can get a narrow and accurate confidence interval. So our conditions here, we're pretty much going to say, hey, like 1, 2, and I'm going to throw in number 3 here, random. So we want to know that we have a random sample. We want to know that our sample reasonably represents the population it came from. That random mechanism is really just getting at, do you use random sampling? Normal. So we want to know, is our sample size going to be big enough for the central limit theorem to kick in? In general, if we are looking at means, a sample size of at least 30 is always going to be good. If you have a sample size smaller than 30, you're probably going to want to have a good idea, hey, is the population fairly symmetric? Is it skewed? What does it look like? Because these things can really factor in whether or not you have a big enough sample size. If you don't know what the population is shaped like, the thing we will typically do is look at the sample. Because if the sample really represents the population, then our sample is basically a miniature population, and however the sample is shaped is how we can assume the population is shaped. So if our sample is nice and symmetric, it usually suggests that our population is probably nice and symmetric. And then 3, we don't know sigma, but we have sample data. So this can mean I have the entire data set. This can mean that we can calculate the standard deviation S of the sample. Whatever. If you have the entire data set, you can calculate S. If you are given S, then you have S. So as long as you have that sample information somewhere, you can use the T methods. So back to our sleep deprivation example. So I'm sorry if this color coding is a little difficult to read here. We have a researcher, they take a simple random sample of 61 students, so this is our N, and they ask how many minutes of sleep do you get on average. I'm hoping they're asking specifically weekends or weeknights. Those are usually wildly different. So those students, they report an average of 455 minutes. So this is in a sample, so this is X bar, with a sample standard deviation of 88 minutes. So this is S. I might write SX some places as well. It just means that the sample standard deviation of the variable X. So calculate a 90% confidence interval using T procedures. So for this, we will have to figure out, okay, T star from a T table with 61 degrees of freedom. Or sorry, 60. So our setup here, it's going to be X bar plus or minus my T star. This T star is going to come from my T table. Degrees of freedom is N minus 1, so it's going to be 61 minus 1. and that's just going to be 60. So this tells me what row to use, and we can talk later about if there isn't a row that goes exactly with our degrees of freedom. And then the column we use, we look around along the bottom of that table to find where it lines up with 90%. So here's my t-star. 88 was my standard deviation for my sample over the square root of my sample size, n, so 61. And all of that is my x bar plus or minus that. So plugging in some math here. 455 plus or minus 18.83. So why did we use this? Because we are using t-methods. We do not know sigma, so we don't get to use, typically we would have used like a z-star of 1.645. We don't get to do that now because we don't know sigma. We have to use a t-star because we only have s. So if I wanted to do this on a TI 83 or 84, they have the same commands. We would use this handy dandy stat button. Absolutely super handy. Although a little dated. I used it way back in the day when I took intro stats. You can go to stat, you can go to t-interval. There are a few options. You can put the entire data set in and tell it, okay, make a t-interval using this list. Or you can give it summary statistics. So you have to tell it, well, here's my x bar, here's my s, here's my sample size. This is my confidence level, so that's the same as 0.90. And then calculate. And then it'll give you right here. So two-part conclusion. This is probably even a bigger deal than the calculation itself to us. So absolutely see that template that we gave in week 1 notes, like reviewing stat 201, because we will look for all of those blanks given in that template. So with 90% confidence, because you have to tell us what level confidence, the mean amount of sleep per night of all students at the given university is estimated to be between 436.17 minutes and 473.83 minutes per night, with a point estimate of 455 minutes per night. Absolutely, we also have these converted to 7 hours and however many minutes. You can convert it if that makes more sense to talk about. Absolutely. But yeah, so we need the confidence level. We need to know, we were talking about a mean. That's the parameter of interest here, is a mean. As soon as you say mean, we're going to follow up with, well, mean what? Well, amount of sleep per night. Okay, the mean amount of sleep per night for what population? Oh, all students at that given university. And then we have our actual interval with units. So between 436.17 minutes and 473.83 minutes. And then point estimate, so that's our actual sample mean with units, which is minutes here. So here's an example here just to practice finding t-star. So suppose we have a scenario where our sample size is 25 and we want to estimate a population mean. So when we say estimate, our head should go straight to, oh, confidence interval. So here we're going to, want to find the t-star value for a 90% confidence interval. So there are two things. So my degrees of freedom, it's n minus 1. So that's going to be 25 minus 1. 24. This tells me what row to use. So, hey, look at this really conveniently cropped table. It has this 24 row here. And then if I want a 90% confidence interval, I'm going to look across the bottom. So looking here, here's 90%. Now I'm going to find where this row and this column meet. So it's going to be 1.711. So if I'm looking at these answer options, it's going to be this one right here. So just looking real quick right off the bat here, if I were looking for a 90% confidence interval, the z-star for 90%, so if I actually knew what sigma was, is 1.645. 1.64 is smaller than that. It cannot be smaller than 1.645. Whatever our answer is, it has to be at least a little bit bigger than that. So know that. That's just a handy way to narrow down your options without before you end up actually solving. So I'll give you a moment here. It's a fill in the blank. So a t-distribution is, and we're talking about the shape, so skewed, symmetric, one of those two, and centered at blank. So here, remember, it's bell-shaped, it's perfectly symmetric, so I can rule out two of those options right away. And then where it's centered, it's like the standard normal distribution. They are both centered at 0. So our t-distributions, they're all centered at 0, and they're perfectly symmetric. They're bell-shaped. So that's it for lesson 2. I'll catch you with lesson 3.